Hey everybody, and welcome to another edition of this year's Knowledge Graph Technology Showcase. I do one of these every year, link down below if you want to see all the other tools that I've reviewed throughout the years. And I do this completely free. I don't get any kickbacks or promotionals or nothing from doing this. I reach out to these vendors and ask them to walk me through a demo, and I will ask questions as we go on your behalf. And I put all of my notes at the very end, so make sure you go and check those out if you are interested in my take about what I thought was very interesting about these tools. And the tool that we are going to be talking about today is that one. All right, and with that, let's go get started.
Hey, and hi everyone. My name is Prashant. I'm an AI engineer at Kuzu. It's an embedded graph database startup based in Ontario, Canada. And in my role, I focus a lot on developer relations and integrating Kuzu with the AI and LLM ecosystem, as well as other use cases that people have with AI and data engineering, looking at this as a property graph. So what Kuzu is it's fundamentally different from what you may have come across in other systems that model what you call labeled property graphs. And in labeled property graphs, you typically have this conceptual schema here in the way that I just described. But what Kuzu provides is a slightly different variant of this. It's called the structured property graph model. And this becomes really important and easy to understand when you actually look at the mappings between these two data models. You essentially have tables in Kuzu that model the actor, movie, characters, and so on. But this is conceptually equivalent to a labeled property graph model. So I'm in an editor window here. And what I'm doing here is I have some code. I have this file. It's a Python script. And essentially, I'll describe the three ways you can interface with a Kuzu database. Now, Kuzu, as I mentioned, is an embeddable graph database. So I'll talk about what embeddability is in terms of how this demo works. And I'll obviously end with some takeaways in terms of what embedded databases can do in the larger scheme of things. But let's look at the data we're working with. We have a bunch of CSV files here on the left. We have actors, names, and other attributes of these actors. We have characters, the name of the character, including their summary, the movies they've acted in, the director names, and so on. So I have a bunch of CSV files that may depict nodes or relationships. And you can easily imagine having extracted this data from some other source, like, for example, Wikipedia or whatever other data sources that you may have in your domain. So what I'm doing here...
I find it funny that you use Wikidata, and yet you're using labels instead of the actual link data that they have in Wikidata.
Yeah, that's fair. That's fair. So what we're trying to do here is it's not necessarily using Wikidata for every use case, obviously, right? Mm-hmm. You may have data sitting in various formats, things like JSON or other databases itself. And you can see here in Python, we have the simple example. You just import Kuzu as a library, and you download or you open a connection to the database, and you begin interacting with it straight away. It's important to define what embedded means in this context. It's nothing to do with vector embeddings or right. The word embedding here has a very different connotation. When we say embedded, all it means is it's in process. So it's basically synonymous with in process. Mm-hmm. And what that means is your application and your database are tightly connected. Mm-hmm. In contrast to a system that is client-server, where your client sits in a different system or completely isolated from your server, and there's a network transport of data across the client to the server. So in this case, the database is right next to the application. Mm-hmm. And if you look at our movie data set, and I'm going to showcase what we construct here, I have a bunch of import statements in the beginning. I'm working in our Python client here. So this is the most common way people may interact with Kuzu in their application, typically the programming language of choice. You may have Python, which is a very popular language, but there are many other language bindings that Kuzu provides, pretty much all the major well-known languages out there. So depending on your application, you can choose to interface with Kuzu using that application's API. So what I'm doing here in these first few lines is I'm essentially creating a database object and a connection to that database. And I'm just going to run this. And you'll see here that I've I basically created a database object and a connection that I can now use to run further commands on this database. And what I'm doing now is basically I've already installed Kuzu. It's just a pip install Kuzu, right? That's what the user friendliness is all about. So once I pip install Kuzu and I run these commands, I'm ready to begin ingesting data from whatever source I have.
So one question, is it appropriate to call it a database? It doesn't seem like it's storing anything.
Well, yeah, you're right. So that's exactly very good question. It's storing something because the moment I ran this command and I create a connection to the object, it's created this directory here on the left called movie_db as per this directory path I gave here. And you can see here there's a bunch of files. There's a shadow, there's a wall, which is a write-ahead log, there's a catalog, there's a data.kz. So all of these are the files associated with the database. Essentially, you maintain a catalog, you have a write-ahead log. So these are all core components of database systems. So essentially, this is what an embedded database is. You're pretty much importing a library, but now the library kind of brings along the database with it.
The database is being generated on the fly. I gotcha.
Exactly. It's generated on the fly. And there's also another option, by the way, to do in memory. So if you did not want to persist to a database, this can function as more or less like an in-memory query engine, where you just bring the database but don't persist the data to disk. Everything runs in memory. So that's an option as well. But in most real situations, your data is large, so you want to persist the data to disk. And that's pretty much why you need a database, because you want to have the ability to do CRUD operations and manage your data over time. So now this portion here is a schema definition. So if you remember, I had a visual depiction of what our schema was. I had the idea of nodes and relationships as tables, which basically are the equivalent of labels in an LPG system. So I'm creating node tables here in these top 5 lines. And as you can see, Kuzu is a strictly typed system. So I'm very explicitly stating the types, the data types for each property I have in my database. And I also have the concept of primary keys in node tables, similar to how you might have in a relational system. And a lot of this is to do with performance, because you want to be able to look up things very, very efficiently and connect them together in a relationship very efficiently so that you can look up via, do your path traversals in a more efficient manner.
But you would have to create the entire graph to do those traversals.
Yes.
Before getting this.
Absolutely.
So this is, and correct me if I'm wrong, this is really powerful for doing a lot of analytics, because the graph,
absolutely,
schema and all of that has been figured out, and then you're just surfacing it here to then run things very quickly.
Absolutely. So when I run this, I've essentially created, you can see here, I'm running each of these commands sequentially because they're separated by the semicolon. And I pretty much run all of these and created my nodes and relationships in empty tables, basically. Now, next step is I point to the files in which I have my data. So I'm pointing to this local directory that I have, and I have all these files. I have a bunch of CSV files here, but in a realistic case, you may have different format files, whatever files they may be. So to ingest these, I have a command called copy from, and this does bulk ingestion from the CSV files. Similarly, it also works on Parquet files and Postgres tables and DuckDB databases and pretty much a lot of other formats. So the idea of copy from is really, really powerful. And this is something that's described in our docs. But when you run this, it pretty much instantaneously ingests this small data set. But copy from is designed for very, very large data sets. And I'll show a very quick demo of that in the next example. But
yeah, I was going to ask, do you know, I mean, I know it's relatively new, but how big is too big for this embedded graph? Because
yeah, that's a very good question. And it's a very common and normal question to have. So I'll come to this at a later point. This is, this just in a nutshell, it's not limited in the conventional sense. It's meant for very, very large graphs.
Okay.
Okay, so now once we finish ingesting the data, we know that we have our database, the data in the database. And what we'll do is I'll run a query in Cypher. So Cypher is the query language that Kuzu uses.
Okay. I'm glad you didn't come up with your own, because that's annoying.
Exactly. Absolutely. No, it's fair. And I think usability is a core feature here. And I think a lot of people already know Cypher, and it's very kind of amenable to SQL. So if you come from SQL, it's pretty easy to learn Cypher. So what I'm asking here is I'm asking the question, give me all the the actors who played characters in the movie Interstellar. And I'm passing the name of the movie title here as a parameter in this query. So it's very, very straightforward to write parameterized queries in your programming language of choice, in this case, Python. And the good thing about Kuzu is it's interoperable. So I'm outputting these results now as a polars data frame. And you may wonder, why am I looking at data frames? Because in most cases, you output results in some structured form. You have either tables or some kind of JSON representation. So data frames are a great way to showcase your output in various ways. So in this case, I'm asking for the names of the actors and the names of the characters. So let me just run this query and showcase what I have here. I had a bit of a typo there, but yeah. So in my result, when I display this result, you can see here on the bottom right, I'm just going to zoom in so it's more clearly visible. So I have this little data frame here that shows these actors acted as these characters in the movie Interstellar. Now, this is, I hope it's clear in terms of the ease of use, right? We started with CSV files. We defined a schema, created our tables, pointed to the files, ingested it very, very rapidly using copy from, and then ran a query to verify that the data is in there and it answers the questions that we have. Right? So this was the initial step. Now, I'll show another way where you can query the database. There's a command line application in which you can just enter Cypher queries. So I've installed the command line in Mac using brew install Kuzu, but depending on your operating system, you have other, it's pretty much available in any operating system, Windows, Linux, Mac, and so on. So on the website, it's very clearly stated how you would install a CLI. But the CLI works like this. You just type in the command Kuzu. Oops, I have a caps lock on. And I'm going to point to the database here. So Kuzu movie DB. So it's basically opening the database that is in my local directory. And now what I'm going to do is I'm just going to paste, or rather, I could type in a Cypher query in the CLI editor. And I'm just going to do that here. So what this is doing is it's basically asking the same question that I asked above, but it's outputting the results now in the CLI.
I can also see why lots of experimentation on your data before doing anything with this is going to be very important, because as we all know, data is pretty messy, no matter how dedicated you are to data cleanliness. So making sure that the data is clean before doing this, I think, is going to be pretty critical.
Absolutely. And that brings me to my next point. So there's a UI in Kuzu that we provide, and that's available via Docker. So if you have Docker installed, I have the simple Docker compose file that I've written here. All it does is it calls this image, the Kuzu/Explorer, which is the name of the UI. And the version of Kuzu that was used here, we're using 0.7.0 here. And I'm opening a read-only connection to the database. So I'm not expecting to make any writes via the UI. I'm only doing reads. And I'm pointing to the local volume, which is the name of this database directory that I have here, movie_db. So if I just run this command using Docker compose up, and I have a UI I can see here. And in this, I can immediately see that I have a schema tab. And the schema tab shows me that I have the schema that I've modeled. It visually shows me that schema that I just showed in my first slide. So when I run this, and I can rerun the same query that I had. So, what is Joseph Cooper's character known for? I can rerun the same query, but this time I'm going to return star instead of individual properties. And now what this does is it actually shows me visually what's happening in the graph. I mean, to make this easier, I can actually just run the most basic query, which is, in this case, match everything. Return star. And you can see here that I have the movie Interstellar. The blue nodes represent, characters. The Cooper family here. This is the Brand family. And you have the actors that played the Coopers.
I am so glad you have something like this. I think that this, I mean, obviously you can just do some quick data visualization in your Jupyter notebook or something else. You can do that too. But I do find it easier when you have everything in one location, because all the time, when you're doing graph stuff, especially with analytics, you think those relationships make sense. And then you get into the visual and you start to see the data then populating in, and you're like, oh, that's not what I thought it was doing.
Features here, there's like a query generation UI powered by GPT, like powered by OpenAI models. So you can actually put in your OpenAI API key here, and you can actually write your query in natural language, which actor played.
Nice.
So it generates a query. And you'll notice here it gave me the answer Matthew McConaughey, because if I actually open the Cypher code editor, this is the query that it generated. And you're right, like it's actually generating the query with the right directions in the relationships. And you might wonder how this happens. This is basically done by passing the underlying graph schema. That is the textual representation of the schema as part of the prompt to the LLM. And the LLM now knows that, okay, I have these node tables, I have these relationship tables. And that's how it is able to get the direction right. The idea of embedded databases being for small data, I think, is something in the past. These are modern analytical large-scale systems that can process billions of records. I have an artificial social network that I've created. What I'm doing is I'm timing the runtime for ingesting the nodes from the raw data files. In this case, my data is in Parquet format. So I have on the left side here, my data organized as Parquet. And you could just as well do this with CSV. I'm just using Parquet because it's a different format than what I just showed. And what I'm doing here is I'm timing the ingestion times for the nodes and relationships. And we'll go through the counts, but I'm going to run some simple queries to demonstrate what the performance benefits of Kuzu are and why it is scalable. So what I'll do is I'll just run the entire code. I'm just going to copy all this code and run this here. And you can see on the right here, it's telling me that I've loaded in the nodes in less than, I think, 2.3 seconds, and the edges in 3 seconds. And I've also run a filter query. So I'll go through what the numbers are in more detail here. So down here, I have some additional queries that I'm running. My first query here is returning the counts of each node label. So how many nodes do I have of each type? So this will give some idea of scale. So when I display this, I can see here I have 500,000 persons, so 500,000 persons, and a few thousand other nodes of cities, states, interests, and countries, and so on. So it's a 500,000 node graph. Now, the relationships is where it gets interesting. I'm going to run another query here that counts the relationships by their label. And I'm going to display their counts as well. So you can see here, I have the follows relationships are quite high. We have 39 million follows. So there are 500,000 persons with 39 million follows relationships between them. And 1 million has interests, and every person lives in a city. So there's 500,000 lives in relationships. So roughly in total, we have in excess of, I think, 40 million relationships, which is not a small data set. It's you could say, in today's terms, a medium-sized data set, right?
Yeah.
But what's amazing here is I'm going to run this query now. How many paths exist in the graph through persons? Like, so I have a person A who follows another person B, who themselves follow another person C. So it's a 2-hop follow relationship from A to C. And I have a filter criteria, which is like a predicate on, the age of the middle and the final person in the path. And I have I could set any bounds on this. In this case, I'm saying less than age 28 for this one and greater than age 30 for the other one. I could choose any arbitrary numbers for this. But as you can imagine, this is a rather expensive query because I have to pretty much enumerate all these paths. Like I have, 39 million follows relationships. And I have a predicate on top of that. So I have to filter down really quickly. So what I'll do is I'll run this in a timer block. It's a 2-hop query with filter, as you can see. And you can see here that the 2-hop query finished in just 0.1 seconds. So it's like 100 milliseconds to run this rather large query. And you can see what's in there. I have 311 million paths that it's computed. So if I wanted to get from person A to person C with these predicate filter conditions, I could have done so in 311 million different ways. So my point is, it's actually able to compute that in this amount of time because there are specific optimizations in the database that allow it to do this. Now, when does it get out of hand and too expensive? At a much, much larger scale than this. Yeah. Right. So when you have literally, I think, tens or hundreds of billions of relationships, we've been actively pushing Kuzu to the upper ends of performance. So we have a blog post that we released on our blog, which is this blog.kuzudb.com, especially our latest release, the 0.7 release. And there is one particular update of interest from a performance perspective here. It's the recursive path finding algorithms. Recursive path finding is basically variable length paths in Cypher, which is by the clean star operator. So you have queries of this pattern where, person knows up to a depth of 10, like you have a path length of 10 between two persons. These queries are really, really expensive. And in many other systems that are not designed the way Kuzu is, you might have timeouts in those systems. What is the state of the art of how graphs can be stored, indexed, and queried? There are a lot of ideas in database research, but the core idea is that Kuzu came out of many years of academic database research. And one of the most obvious ones that people are applying in analytical systems is vectorization, where you treat data in blocks, or like you don't take individual tuples of data, you organize the data in columnar blocks, and then apply more modern vectorization techniques like SIMD and other things to improve the numerical performance of those kinds of queries. There are other more, you could say, theoretical ideas, but implemented in practice in Kuzu. It's quite technical, but essentially factorization is one of those techniques where you reduce the amount of data stored in intermediate stages, and that greatly speeds up computation on recursive queries of a certain pattern. And then morsel-driven parallelism, this is not a new idea, but it's implemented in a lot of other, you could say, SQL database systems, relational systems. But we brought this idea into Kuzu now, where you are able to parallelize a lot of these queries that exploit all the threads and cores available on your machine. So you're essentially getting a lot more out of the CPU or on an individual or single node.
No, that's
And
great.
the most important thing is the novel join algorithms. There's a bunch of algorithms that go into the join side of things, which is when you write a path query, you're hopping from one node to another node to another node. These are essentially done using join algorithms like any other system. But Kuzu implements a lot of the more recent join algorithms in a way that really scales. Scalability aspect, right? Now, I've run the Explorer UI on my social network graph that I just have, which is this schema of persons who live in cities and so on. The part that's really expensive is the person following other persons. So I'm running this recursive Cypher query, and when I say recursive, I mean the clean star operator here in the relationship and a min and max length for the path. So I want to find all paths up to length 5 between two persons whose IDs I know. So I have person A on this side and I have person B on that side. I'm just going to name that. Actually, C is easier to understand. And this is my recursive query, right? So I'm looking all the way up to 5 hops away from the first person. And I can actually run this on a pretty expensive graph. I don't like this color really much, so I'm just going to make this blue. So yeah, when I rerun this, you can see here that I very, very quickly compute the paths between these persons. And just to make things easier, I'm just going to change the labels that I display here. So I'm displaying the names of each person. And as you can see, I have my the IDs that are of interest. I've displayed all the intermediate paths between them. And to explore this graph, I can just very easily double click on immediate neighbor nodes, right? And you can see like each person has a lot of neighbors because they follow a bunch of other people. So rather than having these spaghetti graphs of just displaying a million nodes, this is so much more intuitive where okay, I have 2 persons of interest. I want to find the other people in their vicinity. And I can do things like this where I actually interactively explore this graph. And I think where it gets really powerful is the fact that you can rewrite this query now and identify shortest paths because we provide a convenient syntax for this. Instead of doing the 1.5, if you don't know what the shortest path between 2 individuals is, you can just use the shortest keyword after the clean star. And when you run this query now, you immediately get the response, which is, I have these 2 persons, this is my source, this is my destination, and I have these 4 persons in the middle. So I have a 5-hop path between these 2 individuals. So these kinds of queries are actually specialized in graph database systems. If you try to do this in a relational system, writing SQL, you can imagine how hard that would be. Not only in terms of writing the query itself, but also the computation time can be a concern in those situations. So I think for exploratory and investigative analyses and graphs, I think this kind of architecture as well as the workflows that we are showing, I think that's what's going to enable a lot more innovation and experimentation in the space. And hopefully this acquaints a much larger subset of developers out there with what graphs can do for them. Because I know everybody works with so many different databases and other forms of data, but I think people are talking more and more about graphs these days. And hopefully, this enables some of the experiments that people are running.